Hi. Taylor and Maclaurin formulas are very important tools to solve many problems. In particular, here we focus on computing limits. We illustrate the main ideas and methods on some examples, and you should focus on the ideas rather than the specific example we consider here. Let's start with this simple limit that can be easily computed by using the Hospital rule. But here we want to use another way. So we have the limit for x going to 0 of x minus sin x divided x cubed. It is clear that this is an indeterminate form 0 over 0 type. We know that the denominator is x cubed, very simple expression. Numerator is much more involved because of sign. So we know that it goes to 0, but we don't know how fast it does this. So to respond to this question, we look at sin x, and we use the asymptotic expansion, Maclaurin expansion of sin x, which is, at the first degree, sin x equal x plus little o of x. So this means that if we take x minus sin x divided by x cubed, we can say that this is x minus, we replace sin x by this, divided by x cubed. Here we can do the algebra and simplify a bit this expression, and we arrive to this, O of x divided x cubed. Now the problem of this expression is that we have a 0 over 0 form, but yet we don't know exactly how fast O of x goes to 0. And in fact, this is an indeterminate form. If we rewrite this in this way, we can see, because O of x divided by x goes to 0, times 1 over x squared that goes to plus infinity when x goes to 0. So 0 times plus infinity. So now, to understand what is inside this O of x, we have to look at this O of x and look inside this O of x. The solution to this problem is just adding one more term from the Maclaurin expansion. The next term is the cubic term, as well known, so sin x is x minus x cubed divided 6 plus little o of x cubed. If we replace again this back into the original limit, so we have the numerator is x minus this divided x cubed. Simplifying the expression as before, we remain with the numerator x cubed over 6 minus little o of x cubed divided by x cubed. So 1/6 minus o of x cubed divided x cubed. Now this last term goes to 0, and therefore the limit is 1/6. Let's now illustrate this technique on a more complex problem, where again the techniques are the same, but just with a lot of calculations to do. Here we have this limit. We can easily recognize that this is a 0 over 0 indeterminate form, because when x goes to 0, well, numerator is just a continuous function of x, and so you can just compute the limit by evaluating the function at x equals 0, so e to 0, 1, minus cos 0, 1, so 1 minus 1, 0, and sine 0 is 0 cube 0, so numerator goes to 0. About the denominator, we have a little bit of difference because of this last term. The first part is continuous, so at x equals 0, we have 0 times log 1, which is 0, so 0. About this one, log of x is not defined at x equals 0, and in fact, this would be an indeterminate form, 0 times infinity. However, it is well known that powers are stronger than logarithms, also at 0. So this means that in the product, this product goes to 0. So also this last term goes to 0. We have 0 over 0 indeterminate form. Now to compare how numerator goes to 0 to how denominator goes to 0, we split the problem into two subproblems, discussing first the behavior of numerator and then the behavior of denominator. This is the numerator. Now, to see how fast this goes to 0, we transform all these terms into polynomials thanks to the asymptotic expansions. So, for example, let's start with the exponential. We know that e to y is 1 plus y plus little o of y. This is the first order Maclaurin expansion for the exponential. We replace y equal x squared half, and we get this. For hyperbolic cosine of x, we know that this is 1 plus x squared half plus little o of x squared. And for sine, we have this, x plus little o of x. I'm choosing just the shortest possible expansions to do less possible calculations. So numerator becomes e to x squared divided 2 minus hyperbolic cosine of x plus sine x cubed. Now here you can see that something can be simplified, this one with this one, this x squared half with this x squared half because of the minus here. So from the first two terms, what survives is just this little o minus little o, which is not 0. Because these two little o are just a reminder of different functions that are sharing a common property. They go to 0 faster than x squared, but they are not the same. So I cannot say that the difference is 0. The difference is something that goes to 0 faster than x squared. So that's why you see a little o of x squared. Then I have the x plus little o of x cubed, which is the sine x cubed. Now, according to rules of calculus of little o's, this is, again, x cubed plus little o of x cubed. And in fact, both terms here are little o of x squared, so they can be absorbed into this little o, and this leads to n of x equal little o of x squared, which is nice. It says that it goes to 0 faster than x squared, but we don't know exactly how fast. Now, to respond to this question, we need to look at this little o of x squared and just look inside. Now, where does it come, this? This comes from this little o of x squared, that comes from this, which comes from cosine, and from this, which is that one of the exponential. So if we want to look inside these two little o's, we need to add one term to this expansion. The expansion for the exponential here and the expansion for the hyperbolic cosine here. So that's what we are going to do. So the next term for e to y is 1 plus y squared over 2 plus little o over y squared. That means that when we replace y by x squared half, this is 1 plus x squared half plus the square of x squared half over 2. So it will be x to the power 4 divided 8 plus little o of x power 4. For the cosine, the next term is x power 4 divided 24. While for sine, for the moment, there is no need of doing anything. So the new expression for numerator is now this. This is e to x squared half minus this, which is the hyperbolic cosine, plus the sine of x cubed, which is here. Again, 1 and x squared over 2 go away because they cancel. And what remains are terms like fourth order terms, little o, and this. Now, once we look at this expression, we should recognize that we have x squared divided 4 and 2, 8, and 24 we take common denominator, so this is something like this, 3 plus 1. As you will see, it's not relevant. Then we have a little o of x power 4. And from this, remind that this is x cubed plus little o of x cubed. Now, in an expression like this, the important step is to identify the biggest little o, which is this one, that one with the smallest exponent. Because this one is bigger than this. This means that little o of x power 4 is also little o of x cubed. So it can be englobed into this little o, as well as x power 4, which is a little o of x cubed. So at the end, these two terms just disappear into this little o, and what remains is that the expression can be just simplified to x cubed plus little o of x cubed, which is now nice because it says that the numerator goes to 0 as x cubed. So in fact, if we factorize x cubed, we have a factor that goes to 1. So numerator goes to 0 as x cubed. We now do the same for denominator. We have the first part here, which can be treated in the same way we have done with the numerator. So we start writing the expansion for cosine. We plug into the formula log of cos x equal log of this. Here we recognize that log is log of 1 plus something that goes to 0. So if we call this something y, and we remind that log of 1 plus y, when y goes to 0, is y plus little o of y, we can say that this log here becomes x squared over 2 plus little o of x squared, which is our y, plus a little o of that y. Now, this quantity here is x squared plus a correction of x squared, so that little o will be still a little o of x squared. So this numerator writes, when I multiply by x, as x times x squared over 2 plus little o of x squared, plus this last part, x log x to the power 4. The first one is x cubed divided 2 plus little o of x cubed plus this. Now, what about this last? Here, this is a very, very common error, is to try to use an asymptotic expansion for log of x, which is meaningless because log of x is not defined at x equals 0, so there is no Maclaurin formula for log of x at 0. Well, we know that we have a Maclaurin formula for log, but it is the Maclaurin formula when the argument of log is close to 1, or actually it is the Maclaurin formula for log of 1 plus y when y goes to 0. So it is a way to say the argument of log is about 1. So people usually try to do this. They write log of x, so I create the 1 by adding and subtracting 1, like this. Then now I use the formula log 1 plus y equal y plus o of y, which is correct. So I could say equal x minus 1 plus little o of x minus 1. Now the problem with this formula is that the little o is not a little o. Because, think about, when x goes to 0, we know that log of x goes to minus infinity. Here, when x goes to 0, x minus 1 goes to minus 1. So if you want that this is equal to log of x, necessarily this part should go to minus infinity. So that quantity is not at all negligible here. The contrary is dominant over this one. So this is a wrong calculation that someone continued in this way. Now, what's the right way to do? Well, we know that this goes to 0. Now, the question is here, is this going to 0 faster than this x cubed? If this is true, we could englobe this into the little o, and the problem would be solved. In fact, to check this, we have to verify if x log x power 4 divided by x cubed goes to 0. This can be easily checked by a simple calculation because it is x to the 4 power log x to the 4 divided by x cubed, so x log of x power 4. Now, it is well known, as we said before, that powers are always dominating logarithms at 0. So this is a well-known fundamental limit. It goes to 0. Therefore, we can conclude that numerator is 1/2 x cubed, there is a 1/2 missing here, plus o of x cubed. So it goes to 0 exactly as 1/2 x cubed. We can now complete the calculation of the limit, because the limit is the limit of the ratio n of x divided by t of x. We discovered that the numerator goes to 0 as x cubed, and the denominator goes to 0 as half of x cubed. So when we divide the two, we can cancel these x cubed, which are responsible of the 0 over 0 indeterminate form. And what we get is just a finite limit equal to 2. That's it. I hope that this video has been helpful for you. Now, what you have to do is just to practice and practice and practice about these techniques. So computing limits like these ones, for instance. And if you want to have a more theoretical exercise, this is a very nice problem. Good job.